Now we are going to start our first session. Here our speaker is Professor Prasanta K. Jana, received MTech degree in computer science from University of Calcutta in 1988 and PhD from Jadavpur University in 2000. Currently, he is a professor in the Department of Computer Science and Engineering, IIT ISM Dhanbad, India. He has contributed 140 research publications in his credit and co-authored 6 books and co-authored 2 book chapters. He has also produced 7 PhDs. As a recognition of his outstanding research contributions, he has been awarded senior member of IEEE in 2010 and Canara Bank Research Publication Award in 2015. He is in the editorial board of 2 international journals and acted as referees in many reputed international journals. Dr. Jana has acted as the general chair of the international conference RAIT 2012, co-chair of national conference RAIT 2009, and convener of the workshop WPDC 2008. He has also served as advisory committee and program committee members of several international conferences. His current research interest includes wireless sensor networks, cloud computing and big data clustering. He visited University of Aizu in 2003, Japan, Las Vegas, USA in 2008, Imperial College of London, UK in 2011, University of Macau in 2012, and Hong Kong in 2015 for academic purpose. I request Professor Jana to deliver his talk. Thank you, sir.
Thank you very much, Dr. Rasmi Ranjan, for my long introduction. Well, I always feel pleasure when I get the invitation from one of my best scholars, Dr. Sanjay Panda, and of course, behind that there is a tremendous role of Dr. Rasmi Ranjan. And my pleasure is to share some kind of the knowledge which I actually obtained through the research in the field of the fog. Today my talk, it will be an overview of the fog computing. I will start, followed by the architecture, and then I'll go for the applications and research challenges finally. So let me share my screen. Is it shared? Hello?
Not so far, sir.
Okay. How is it?
Yes, sir. Now you can open your slides, sir, your PPTs.
This is visible?
Yes, sir. Now it is visible.
Yeah. Thank you. So the title of the talk, it will be the fog computing architecture, applications and research challenges. This is my institute where I work. And here the organization of my talk. I'll have a background and motivation behind the fog computing, fog architecture, and very important aspect regarding the fog computing, that is the resource management and task uploading. I'll say something about the applications of the fog computing and followed by the open research challenges. As you all are aware, the world has now witnessed a tremendous growth of the IoT devices. Millions of devices are now connected through internet. The devices like the smartwatch, your smartphone, laptop, tab, and many more. They are now connected through the internet. Why it is? Because we require a lot of services, number of services in the domain areas like autonomous vehicles, smart home, smart city, smartphones, healthcare, and which is very much important. Whenever we try to obtain some this kind of the services must be provided to all the users instantly, securely, and reliably. So we require suitable technology for that. I'll come to that particular technology, but before that, let me first express some kind of the facts. It says that International Data Corporation expected that sensor-enabled objects connected to network will rise to 30 billion by 2020. The number of connected devices will rise from 50 billion to 1 trillion. It is also estimated that there will be 237.1 million wearable devices by 2020. The number of connected devices per person is going to be on an average 7, that is 6.58 on by 2020. Current smartphones contain on an average more than a dozen of sensors. So what is the implication? We require a huge storage and huge processing power. So what will be that particular technology? So the technology, it will be your cloud. Now, the cloud, it will be the supporting technology to provide this kind of the services in the domains I uttered. Why it is? Reason is that the cloud computing actually provides the massive data storage, massive processing power, and it provides the cost-effective solution with security and reliability, and of course 24 by 7 hours service time. Thus, the cloud computing becomes an attractive choice for massive processing and storing a high volume of data. So what is the consequence? 90% of the global internet users are now dependent on cloud-based services. But there are a number of limitations of the traditional cloud computing. So we require instant services. So some of the applications really do not tolerate any kind of the delay. But if you use the traditional cloud computing, because of the physical distance between the cloud and the end devices, your smartphone, laptop, etc. So because of this physical distance, it actually causes the latency problem. So we may not get the streaming from the cloud, directly from the cloud, with a in a full-fledged manner. It may be corrugated, it may be delayed streaming, and we feel inconvenience enjoying the film, enjoying any other kind of the video clips, and this creates a hindrance to sensitive applications such as digital management, healthcare, etc. Another problem is that due to large number of applications which are actually run by the cloud server, right, there is a huge traffic congestion. And again, the data centers have lot many high-end servers, lot many, I want to mean that maybe the hundreds or even the thousands of the high-end servers. Since they are on 24 by 7 hours, that's why energy consumption, it will be huge. And whenever energy consumption is more, and then in that case, it increases the carbon footprint in the atmosphere that causes the global warming. So they are all the limitations of the cloud computing, right? So what will be the solution to mitigate this particular the problems which will be faced by the cloud computing? I'll come to that, but before that, let me also say IoT environment is also constrained with respect to the bandwidth, processing, memory, and energy. So we require the cloud services instantly, securely, and there is a physical distance between the IoT device and cloud. Because of this physical distance, it actually suffers from the latency problem. And the latency, I want to mean, that is the time for transferring the data from the device to the cloud, maybe in the form of the request or maybe some kind of the data, and then analysis of that particular data, it will taken by the cloud servers, and again the result that must be transmitted back from the cloud to the devices. So all this time, if we just sum up, this actually causes huge latency. That's why should we not put a middle layer in between the cloud and the IoT? It's okay, so that instead of downloading or uploading directly from the cloud, we can provide the services of the cloud nearby the edge devices or the IoT devices. That's why you have put up a middle layer in between the cloud and IoT devices. The main purpose, we want to bring the services of the cloud at the edge of the network, that is very close to or the nearer to the IoT devices. I'll come to that particular how it actually works. So the idea of the fog computing is to extend the cloud nearer to the IoT devices. And the fog, I want to mean, that is the from core to edge computing. Why it is so? Because fog is basically a cloud close to the ground. You know, the cloud actually at the on the sky, but the fog, it will be very close to the ground. So fog is a cloud close to the ground, and the term fog comes from the words from core to edge computing. Note that fog is not a substitute to the cloud, but it is basically a complementary to the cloud. Fog alone cannot work. It cannot work standalone. So it always works as a complementary to the cloud. Wherever there is a cloud, then only there is existence of the fog. Okay. So what is the primary aim? We are supposed to solve the problems which are faced by the cloud computing due to IoT processing. That is the main goal of the fog computing, just to solve the problems faced by the cloud computing during IoT applications. Now let us see that how does it, so what is the definition of the fog computing? So the fog computing is a highly virtualized platform that provides computing, storage and networking services between end users, that is the IoT devices or end devices you can say, and the data center, that is the servers of the data center of the traditional cloud computing. So this is the proper appropriate definition of the fog computing. But you know, fog computing has other definition as well. I have picked up this definition. I feel that this is the most appropriate definition according to my opinion. It again says that fog computing is a highly virtualized platform that provides computing, storage and networking services between end users and data center of the traditional cloud computing. You can note at the bottom layer all the IoT devices or end devices are there. Maybe your camera, smart camera, smart watch, maybe the laptop, maybe the tab, your smartphone, etc. And there is a formation of the mini cloud. So these mini clouds that consist of huge number of nodes, and these nodes are nothing but your routers, maybe the access points, maybe the gateways, maybe your surrogated server, like this. It's okay. So, and all these devices that we are able to virtualize, I want to mean, whenever there is a physical server, we are able to create a number of virtual machines at the fog layer as well. Physically it may be limited, but whenever we go for the virtualizations of, then we are able to create number of virtual machines from this physical collection. Okay, and it creates a mini cloud, and these mini cloud, they actually exist very close to the IoT or the bottom layer IoT devices or the end devices, and cloud, it will be your just above layer. And you can have a note that we do not require to upload directly to the cloud, or we do not require to download directly from the cloud. So that particular data may have already been stored in some of the fog node. So rather than uploading or downloading directly from the core cloud, we are able to do so from the nearby fog nodes to provide some kind of the services to the end users. And not only that, whenever there is a creation of this mini cloud very close to the IoT devices, the number of services which are really provided by means of the cloud can also be performed by means of these fog nodes. Okay, so the task which are actually sent to the cloud, we should actually take that particular task to be executed by the nearby fog nodes. That way, latency problem we are able to solve it. So, how does the fog actually works? A very large number of geo-distributed devices forms a mini cloud at the edge of the network, as I already shown in that particular previous figure. Instead of always upload or download data from our core network, the edge devices which are in proximity can obtain data from other users through direct link and adjacent small cell networks. In addition, the edge devices in fog network release some of their resource like computing and storage capacity to support demands of their neighbors. Only the task that is not well handled by the edge devices are sent to the core cloud part for further processing. So this is the way the fog really works. And here you can see connectivity between the end devices and then fog node. This is the local area network. It actually indicates that how close the fog nodes are to the end devices, because they are connected to the local area network. Say for example, all the computers in a department, they are actually connected through the LAN, and it actually indicates the proximity of all the computers within that particular department. Whereas the connectivity between the fog nodes and your cloud servers, it is WAN, that is the wide area network. It's okay. And you just note this LAN connectivity, it may be the wired or it may be Wi-Fi or uh, other kind of the connectivity. It's okay, because of the very close distance between the end user devices or the IoT devices and the fog nodes, right? So this is the what about the connectivity. You look here, it is WAN. We do not require to directly upload or download. It will be always from the fog node. If some kind of the replicas of the data do exist here, if it is not found, then we are able to go to the cloud. Actually, the request, it will be made to the fog, and fog will bring that particular data from the cloud to that some of the access point, and that access point will deliver that particular data to the requesting end users. So that way actually the fog works. So we can think that uh, fog nodes, they actually form a mini cloud, and that particular layer, it will be the intermediate layer which actually exists in between the cloud server, means cloud, and the bottom layer, that is the edge devices. But whenever we count the number of devices, so at the bottom layer, this is the end devices, that will be in the order of billions, whereas the number of the fog nodes, it will be in terms of the millions. But as compared to the fog nodes and the end devices, there will be uh, cloud servers, it will be in the number of the thousands. It's okay. And you can see like depending on, as the numbers decreases, cost also increases. Is it okay? So the cost of the high-end server, it is very high rather than any fog nodes. And the what kind of the fog nodes are there? I said gateways, surrogated servers, or maybe the access points, like this. They are all the fog nodes, and their cost, it will be higher than the end devices. say let it be your laptop or let it be tab, smartwatch, smart camera, etc. So this decreases in terms of the number, but the cost really increases. It's okay. So in the IoT environment, we require both cloud and fog. Fog layer is used for intermediate processing and transit storage. Sensor data is processed in the fog before it is sent to the cloud. Okay. Now there is a sharp wall between the cloud and the fog. So if we consider they are all the features, here is the traditional cloud computing and this is the fog computing. Most notable with respect to the computing model, whenever the cloud, it will be centralized because all the servers they are confined to a single location, or the data center confined to the data center. Although these days there is a concept of the multi-cloud environment, but if we consider a single cloud, all the servers, they actually belong to a single data center. Whereas for the case of the fog computing, the computing model, they are actually distributed because the fog nodes are distributed here and there. So distributed fog nodes are controlled in both distributed and centralized manner, but usually this is in the distributed manner. It's okay. So it actually follows the distributed computing, whereas the cloud, it will be your centralized. Now deployment cost, since there is a huge number of high-end servers, so the cost, it will be really high for the case of the cloud. But here depending on the types of the end devices, depending on the type of the fog nodes, like access point, it is, or let it be router, is much lesser cost than the high-end server. So the cost for the fog nodes, it will be really low. And then the resource optimization for the case of the cloud, it will be the global, whereas for the fog computing, it is local. Size, the data center cloud size, it is enormous. Thousands of the high-end servers, they actually keep it, especially for the public cloud, let it be IBM or let it be Microsoft Azure or let it be Amazon EC2. So they contain huge number, their data centers actually gigantic and contains a huge number of servers. So that's why the size of the data centers, especially for the public cloud, it will be huge, but the size of the this is very small. In the fog layer, smaller, however, a large number of small fog nodes form a large fog system. So the size, it will be although small, but the totality, it will be very large fog system. It's okay because it can create, with the help of the virtualization technique, we are able to create huge number of like fog nodes. Mobility management for the case of the the cloud, it says that easy, but fog nodes mobility, that is actually challenge in the recent research work, that why should we not move the fog nodes from one location to another, like the IoT devices or end devices. But there is a challenge. If we can make the fog nodes movable, then we can provide a number of flexible services to the consumers or the stakeholders. Latency for the case of the cloud, as I already said, latency, that is the delay, it is high, but for the case of the fog computing, it is very low. It's okay. And that is the reason, because of this particular feature, really the fog computing exists. Just to mitigate the high latency, we can employ the concept of the fog computing, although computing or networking, etc., that facilities are also obtained by means of the fog computing from the cloud. Operation, it will be operated by large companies. Large companies, as I already told, that Microsoft, let it be your IBM. So cloud data centers are really operated by means of the large companies. But for the case of the fog nodes, that may be owned by means of the private companies, maybe the smaller than the large companies. Reliability for the case of the cloud, it is really high, but fog nodes reliability, that is very low. Maintenance, of course, this is high for the case of the cloud. Generally requires no or almost a little human involvement. And application cyber domain applications, but for the case of the fog, support both cyber domain and cyber physical application. Most importantly, time critical applications, it is really served nicely by means of the fog computing. So they are the differences between the cloud and the fog. Now, what are the characteristics of the fog nodes? The storage, as I already said, this is transit. This is not really permanent. It's okay. And computing facility to process data before it sends to the cloud. It can process that particular data. The data, it will be processed by means of the fog nodes, but it must send a copy of that particular result or the data to the cloud itself. And why? Because we need to take a quick decision for it. Network connectivity to connect end devices and fog nodes. And examples of the fog devices, as I already told, servers, routers, switches, and access points, etc. Okay. Now, what kind of the data we are supposed to handle by means of the fog computing? It may be the very sensitive data, maybe the less time sensitive data, or maybe the non-time sensitive data. For the very time sensitive data, data which should be analyzed within a fraction of second, say for example, surveillance system or the fire detection. It's okay. If we do not take the quick decision, then there may be a kind of the devastation. Say for example, fire detection. We require the very quick decision. It's okay. So this is very time sensitive data. Less time sensitive data which should be analyzed after a second, after second or minutes. For example, non-critical healthcare data. It's okay. I did not say that some healthcare data is also very critical. It's okay. Say for example, we require immediate attention to the patient. I am saying non-critical healthcare data, that will be the less sensitive. That is one of the example. And then non-time sensitive data which can wait for hours. So let it be prediction of the air pollution. It's okay. We have collected the data from the sensors and that we send to the cloud server, and cloud server actually analyzing it to predict what will be the tomorrow's rainfall. How much millimeter, whether it is 75 millimeter or 100 millimeter or 0.5 millimeter. So we can wait for hours. It's okay. So data which can wait for hours, day or a week. For example, prediction of the air pollution. It's okay. Air pollution, what will be that? That particular level. It's okay. And then customer purchase behavior. Okay. So they are basically non-time sensitive data. Now, features of the fog computing, it really has low latency and location awareness, supports geographic distribution, end device mobility is possible. End device mobility, it is not the fog node, right? Then capacity of the processing, high number of nodes, and it can have the wireless access. As I already told, we are using the LAN, but that LAN connectivity, it may be the wired, it may be the wireless as well, because of the proximity between the end devices and the fog nodes. Then it can deal with the real-time applications. And of course, this is the heterogeneity. Heterogeneity, I want to mean heterogeneous kind of the end devices we are able to get it. So heterogeneous, I want to mean your camera, and then watch, let it be phone, etc. And again, among a specific class, let it be smartphone, like there may be different network connectivity, right? Someone maybe the Vodafone, or someone has the BSNL, another maybe the that Airtel, etc. And heterogeneity in the devices are also there. Your smartphone may be from the Samsung, maybe from the other kind, Viva, or any kind of type. So they do have the different kind of the configuration. So heterogeneity is also there, both for the end devices as well as the fog nodes, right? So they're all the features for the case of the fog computing. Now, fog system research, we are able to grossly classify into two specific area. One, it will be the architecture side, another it will be the algorithms. In the architecture, let us first go for the application specific architectures. In that case, it will be the smart transportation system or connected vehicle applications. Similarly, healthcare applications, and architecture has also been developed number of architectures for the smart city applications. And another, it will be the end user applications, which are also known as agnostic architectures. It may be the depending on the resource management, depending on end user application provisioning, maybe the cloud and fog federation, right? And finally, depending on the communication issues. So they are all right. And whenever you enter into the algorithm side, most importantly, which is basically known as the task uploading, that is huge, huge amount of research work have been carried out. So this is the algorithms for the computing. One, it will be the resource sharing, then task uploading and load distribution. Huge research have been carried out, and here it is the task scheduling. Although task scheduling is there for the case of the cloud, but task scheduling can also be there for the case of the fog as well. Then this is the algorithms for the content storage and distribution, algorithms and energy consumption, right? And depending on the type of the applications, we are able to develop the algorithms as well. So specific end user application algorithms, so healthcare or other applications, as I already told here. It's okay. So these are the two important parts where the people or the researchers carry out their research work. One, it will be the architecture side. They design architecture and go for the test bed to measure the performance of their designed architecture. Another, it will be the algorithm side, and in the algorithm side, task operating is the has given lot of priority. It's okay. I'll come to that, both architecture as well as the algorithms now. That's why in my speech I have actually divided into architecture side and as well as the your resource management. Okay. Now, all of a sudden, that fog computing concept hasn't been developed. Before that, some related technologies developed. They are basically known as cyber foraging, cloudlet, and parallelly make. Make is actually parallel concept with your fog computing. People say they are all belong to the class of edge computing. I fully agree, because they all provide the services to the IoT devices near the, and they, as they are deployed near the edge of the devices. It's okay. So what is that cyber foraging? This is the resource limited mobile devices send its heavy computational tasks to the server known as surrogated server. It's okay. For the case of the cyber foraging, resource limited mobile devices, it's okay, send its heavy computational task to the server known as surrogated service. It's okay, because your mobile device may not have that much computational power. Okay. And for the case of the cloudlet, cloudlet is based on the virtualization concept. Run one or more virtual machines in which mobile devices can upload components for expensive computation. And finally, it will be the multi-access edge computing, which is also known as make. Focuses on the applications that are better suited for both mobile and non-mobile network edge, can use other technologies apart from the virtual machines, can work in standalone, and can connect to the cloud. This is most important difference between the make and the fog. The fog alone cannot work. It's okay. I'll come to that particular differences between all these three technologies. There are common parts. This is the relationship between the fog cloudlet and the make. This is your fog computing. This is the multi-access edge computing, and here is the cloudlet. There are some common features. It's okay, but there are differences as well. So what are the differences? I'll come to that particular point. So with respect to the three features, one, it will be the application. While the cloudlet supports the mobile uploading, make actually focuses on the applications that are better suited for both mobile and non-mobile network edge. Whereas the fog, it supports a wider range of the latency sensitive applications for resource constrained in devices. For the virtualization, cloudlets only depends on the virtual machine, but make can use other technologies apart from the virtual machines. It's okay. It can use other than the virtualization as well. Fog computing, again, other virtualization techniques can be also used. So you can say, with respect to the feature virtualization, make and fog really parallel. It's okay. They do believe it. Operational mode, it can work standalone. Cloudlet, that can work standalone. Make can also work standalone. Whereas fog cannot work standalone. It actually requires the support of the cloud computing. And that's why I told fog is a complement to the cloud. So fog is not the substitute to cloud. Whenever there is a cloud, then only concept of the fog comes. But for the make without cloud can work standalone. So without use of the cloud, the make really exists. It's okay. Similarly for the case of the cloudlets as well. Okay. So they are the basic differences between the related technologies, especially for the cloudlets, make, and then fog. It's okay. Cyber foraging, that is the old technology. Only I didn't express here. So I'll go for some kind of the use cases. I'll show you that how the fog that can be used in the two different cases. First one, it will be fire detection, and second one, it will be your content delivery system. It's okay. Sorry, that will be for your content delivery system. Now I'll go for the first one, content delivery system, followed by the fire detection system. Now, what is the content delivery networks? This actually a network, a content delivery networks consist of origin servers. It's okay, and then surrogated server as well. They are also basically known as replica servers. So original, all these surrogated servers can have the replicas of the original data, right? So the content delivery system that consists of the origin servers, surrogated servers, and a controller. The origin servers store the original content, but the copy that can be stored in the surrogated server. That's why this content is replicated on the surrogated server. Whenever there is a request from the end user, the controller selects the most appropriate surrogated server which provides the service to the requester. It's okay. So that way a CDN actually works. Your original data, it will be stored in the origin servers, and a replica of that data is really stored in the surrogated server. Whenever there is a request from the users, then the controller selects the most suitable surrogated server to provide the service to the customer. Okay. So first case is about the video streaming in the content delivery network. You know that here is a system, origin server I have shown you. I assume the data that has already been stored, the replica of that original data has already been stored in the surrogated server. It's okay. Now suppose the John wants to enjoy some video clip. Okay. So he made a request to the let it be surrogated server. What the surrogated server will do, the surrogated server actually sends that particular data to one of the access points which will be closer to the closer to John. So that's why that particular video stream has been stored in this access point, and from there the John can have the video streaming. It's okay. And note that John is actually moving from one location to other location. So whenever it is moved, it has already been started streaming to John. In the meantime, Lena has joined. So Lena should not, whenever it actually sent a request, her request, it will go to the access point. Then access point can see that particular video is already available with it. So it starts streaming. So both John and Lena, they can enjoy the video streaming. In the meantime, the John actually has already changed his position from the access point to this particular location. And then seeing that controller transmit that particular video stream to the another access point, which is really closer to John in the new position. So John is actually getting the video streaming from the access point B, and Lena is also getting the video streaming from the access point A. And note that here number of latency issues have been actually mitigated. First of all, the John has not made a request directly to the origin server, because that particular data has already been stored in the surrogated server. And whenever there is a request from the John, surrogated server sends that particular video streaming to the access point. That way latency that can be mitigated, right, can be reduced. And once again, whenever that particular video has already been stored in the access point A, and Lena although made a request to the surrogated server, but she is getting directly from the access point capital A. So for that, again, video streams should not be replicated from the surrogated server to the access point, because it is already available. And another thing, whenever the John is actually changing his position, then again the surrogated server, it is not actually making a replica to the access point, since the B exists very close to A, because they are the fog nodes which will be further from the surrogated server. So that's why this transmission, a replica transmission, the data transmission, it actually takes less amount of time, right? So delay also that can also be saved like this. Okay, so a huge number of delay we are able to reduce by means of the content delivery network system. It's okay. So that way actually the fog. So this is our fog layer, and this is your cloud startup, and this is the end users. So this is a very good applications. We frequently use the we use we are very much fond of Netflix. We very much fond of your Prime Video, right? So whenever we click to enjoy some kind of the flip, this content delivery system is actually implemented. Rather than getting everything from the cloud, we are actually getting from some kind of access point, and that way we are able to reduce the latency. So this is one of the great examples of the use of the fog computing. My next example, it will be the fire monitoring and detection. Okay. So in the fire and monitoring detection, you know that it may be a city or maybe a forest area, and this is the contour of that particular forest, and there may be a chance of fire. And you know that whenever there is a fire in the forest, um, if there is a delay, say let it be an hour or let it be a few hours or even the few minutes, it can actually make a devastation. The whole forest can be fired off. It's okay. So we are supposed to take the very strong decision, right? And in that case, what will happen? Usually, we are able to put a wide number of sensor node. We are able to deploy inside this contour. So all the sensor node, they can sense some kind of the data, let it be wind speed or let it be moisture content or let it be your temperature, and these three data they can send, each sensor node can send that particular sense data to the base station, which is also known as sink, and through the sink, with the help of the internet, we are able to collect all this data to a server. It's okay. So whenever these three data that can be assembled to the server, it actually performs some kind of the analysis depending on the intensity of the moisture content or wind speed or temperature. It can judge whether it exceeds some kind of the threshold value or not. Whenever it exceeds a threshold value, then it can find that there is a chance of fire. It's okay. Then it actually dispatched one firefighting vehicle It's okay, and then it goes to that particular area and then put up that particular fire. But you know that there is a huge time delay for this kind of the processing and dispatching the firefighting vehicle. Reason is that you need to collect huge data from the all sensor nodes to collect it in the server. Server will perform some kind of the analysis, and then out of number of vehicle it can select some kind of the suitable vehicle and can trigger to reach that particular point to fire it. So this is the traditional relay sensor network tradition. But for the case of the fog, we are able to do the first of all, you can have it the three things. One, it will be the fire detection. Next, it is the firefighting strategies, and finally, it is the robot dispatcher. So these three processing that must be taken care appropriately. It's okay. We need to detect the fire. It's okay. We have already collected. So let it be. All the data has been collected from the sensor node to the cloud. So we need to detect the fire. So this fire detection just for a simple calculation whether it exceeds some threshold value or not. So this fire detection that will be taken care by means of the fog node. Only the firefighting strategies that out of number of robots, it's okay, firefighting out of number of robots, which particular robot who or how many robots it will be dispatched to that particular fire area to put up the fire. This is the firefighting strategies. It's okay. So this decision is complex. This decision is complex. How many robots to be dispatched and what will be their location, etc. So firefighting strategies is much more complex. So that can be taken care at the cloud startup. But again, robot dispatcher, it is very simple thing. It's okay. It can simply trigger that, okay, whenever just that 4 or 5 robot, it will be dispatched to that particular area. So this one. So the simple processing, that is the fire detection and the robot dispatching, that can be taken care by means of the fog nodes because they have limited power. But firefighting strategies, how many robot to be dispatched and which particular robot to be selected and what would be their location to reach. So these complex thing, it will be taken care by means of the cloud. So rather than putting everything on the server, these tasks, the three tasks we have actually divided into we have distributed among the fog nodes and as well as the cloud server. Whenever the fog nodes will deal with the fire detection and the robot dispatcher, at the same time the firefighting strategies, it will be not at the same time, firefighting strategies, it will be taken care by means of the cloud. It's okay. So first one, the fire detection, it will be taken care, right? And then it goes for the firefighting strategies, it will be taken care by means of this, and then here it is. So this 1 and 1 that belongs to the fog node, and 3 or 4 it will belong to the cloud. That way we are able to solve the problem very quickly with the help of the fog nodes. It's okay. Now I'll go for the architecture. Number of architecture actually have been proposed for the case of the fog computing. It may be the layered architecture, it may be the 3-tier architecture, it may be the multi-fog node architecture, multi-layer of the fog nodes. First of all, the most common is 3-tier architecture. In the tier 1, that is the bottom layer, it will be the Internet of Things or the end devices. This layer contains IoT devices, end user smart devices, for example, smartphones, tablets, and smart cards, smart vehicles, and smart watch. They are also known as the terminal nodes. See, this is in this particular figure. So they are all the terminal nodes. It's okay. This is the bottom layer. This is the tier 1. In the second tier, it will be your fog layer. This is the fog computing layer comprised of the network devices. What kind of the network devices? Router, gateway, switch, access points. We have taken the name. These fog nodes can collaboratively share storage and computing facilities. It's okay. So this is the fog layer, and here it is the switch, access points, maybe the surrogated server as well, etc., etc. Okay, and then you have the third layer, that will be your cloud, that is the top layer. Traditional cloud servers and cloud data center reside in the topmost tier. This tiers has sufficient storage and computing resources. Hello, Sachin. I'll have a look of it. I'll talk to. I have some presentation है. मैं आपसे बात करता. Sure, sure. I'm sorry for this intervention. Sanjay, are you there, na? Hello.
Yes, yes, sir.
Yeah, just a minute.
Please, yes, sir. Please.
Is it visible, Dr. Rasmi Ranjan?
Yes, sir. It is visible, sir.
Okay. So at the third tier, it will be your cloud, traditional cloud servers and cloud data centers that reside in the topmost tier, and this tier has sufficient storage and computing resources, as I already spoke. And this is the cloud, and here it is the fog, and this is the end devices. This is common, that I already shown to you. The next, it will be the layer architecture, like the computer network. You see, at the bottom, it will be your physical and virtualization layer, contains TNs or the terminal nodes and virtual sensor node. Then monitoring layer handles service request and energy consumption issues. Pre-processing layer, it will be the data filtering and trimming. And then temporary storage layer, this is the security layer. And finally, it will be your sense data with the help of the transport layer. So this is the layer architecture of the fog computing. This architecture is also proposed for the case of your fog computing. Okay, now this is the combined this is the architecture for the combined fog and cloud. You know that the bottommost layer, it will be your terminal nodes, like the three-tier architecture, but in between, rather than a single fog layer, we can have multiple fog layers. Say for example here, first of all your terminal nodes, right, IoT devices, and in the next fog layer 1 and fog layer 2, and at the bottom, at the top, it will be the cloud. It's okay. But what is the intention to deploy multiple fog layers in between the cloud and the terminal nodes? Reason is that the first fog layer, because of the very close proximity with the terminal nodes, it can have low access delay. Am I right? But whenever the second fog layer, it actually exists slightly higher than that of from the terminal nodes, because it actually exists above the fog layer 1. That's why, yeah, it can provide the services with medium access delay. Am I right? And for the cloud, it will be at the top. That's why it is high access delay. So depending on the type of the applications, some kind of the fog architecture has also been designed whenever multiple fog layers really exist in between the cloud and the terminal nodes. You know, the three-layer architecture, that is fine. One, it will be the bottom layer IoT devices, and then after that there is a fog layer, right, and above just only the cloud. But in between the cloud and the terminal, depending in the nature of the applications, where it will be very sensitive to delay, or it will be low sensitive to delay, or it will be high sensitive to delay, depending on the type of the applications, we are able to increase the number of fog layers in between the cloud and terminal nodes. It's okay. So this is the actually an architecture of combined fog cloud. Okay. Now, so this is what about the architecture should I said it. I'll come to the next important point, that is the task offloading. But I'll go for some kind of the frequently asked question. Fact. First upon, what is task offloading in fog computing? What I told you for the case of the fog node, whenever a task is really generated by means of a terminal node, it may not be directly executed by means of the cloud server. It's okay. So some part of the job that can be executed by means of the terminal nodes itself, some part may be sent to the fog nodes, and if the fog node cannot execute that particular part, so it can send to the cloud. It's okay. So IoT device cannot directly send everything to the cloud. It can handle by itself. If it is not handled by itself, then it can send some kind of the task like to the fog node. So the task execution that is actually distributed among the three entities. One, it will be the end device itself, then it will be the fog nodes, and it will be the cloud. Now various kind of the task offloading has been actually taken care. This is the task uploading. I want to mean sharing the task execution between the end devices and then fog nodes, or between the end devices, then fog nodes as well as the cloud, right? Or simply by means of the fog only. So end device is unable to process it, then it sends the data to the fog and it executes the task on behalf of the end devices. It's okay. So what is the actual term? What do you mean by the task completing in fog computing? Note that the people always take it granted transmission of that particular task to the fog node, that is basically known as task offloading. It's not like this. It actually refers transferring part of the TN's task to other entities such as fog nodes or cloud server, so that they can be processed and send back the results quickly to the TN. So only transferring the task, this is not the offloading. So transferring the part of the task to the fog node or the cloud, and its process, and again send back the result. The whole process is actually known as task offloading. So offloading the task doesn't mean only the transmission of that particular task to the cloud or to the fog node. Whenever it transmitted, then the fog node executes it and sends back the result. So this whole process, transferring the task or the data, execution by means of the fog node, and sending back the result, the whole process, this is basically known as task offloading. So what is the main goal? The main goal of the task offloading is, of course, to reduce the burden of the cloud servers. It's okay. We do not put lot many burden. As I told you, if everybody will send the task or data like to the cloud, there is a congestion. It's okay. And not only that, it requires a huge execution, and energy consumption is also to be increased. So in order to reduce the burden of the cloud server, that's why you have introduced the fog layer, right? So this is the main goal for the task uploading, just to reduce the burden of the cloud server. Why task uploading? Because the tasks may be very large and competition intensive, and the TNs may have limited processing power. So this is the reason why do we really record the task uploading. What is the main reason? Task may be very large and then computation intensive, and your TNs are actually have the very limited processing power. TNs has no processing power. Smartphone, how much processing power have? Of course, depending on the type of your smartphone, but all the smartphone may not be powerful enough to process your request. It's okay. So these are all the frequently asked questions about the so other parameters. So let it be, what would be the QS parameters to be fulfilled? First of all, most important, it is minimum delay. It's okay. Task to be executed by means of the fog computing with minimum delay, and that is the main reason why should we employ the concept of the fog. and then minimum energy consumption. Next, to the delay comes into the picture, that is your energy consumption, and finally, of course, the cost is okay. Although other QS parameters are also involved, number of researchers actually have considered during their proposal of the task uploading algorithm. Is okay. Now, what are the advantages of the task uploading? It can have the proper utilization of the ideal resources, that is the load balancing, then proper energy management, and of course the proper latency management. It's okay, they are all the advantages. So service allocation and resource management, so it becomes an important issue whenever there exists so how to decide which task or service should be processed in the fog layer or be forwarded to the cloud. That is most important question behind the task uploading. Which particular task should be processed in the fog layer, or which one it will be forwarded to the cloud? This is the most important question for the case of the task uploading. In the fog computing literature, this is also referred as service allocation and resource management. It's okay. Next, so how to find out the target fog node? Your number of fog nodes and your number of end devices. Whenever single end device will wants to upload the task, so how we have to decide which particular fog node that the task to be uploaded. So the following policies we are able to: number of fog nodes exist and a single end device wants to upload the task to a fog node. So what will be the different policies? First, it will be the randomly. We are able to randomly select the fog node. It's okay. A fog node is randomly and uniformly selected without considering any other factors. Or we can have the lowest latency policy. I want to mean we are supposed to upload that task to a fog node which actually provides minimum total latency at the current state of the system. That particular fog node, it will be selected. Or we are able to upload that particular task to the fog node which has maximum available capacity policy. It's okay. So these are the basic three policies we are able to adopt, although some intelligent policies have also been made, and that way the task uploading algorithm have been actually proposed it. So resource management, energy consumption is very much important. So the first part I have completed. The first part, it will be your service allocation and resource management. Next come in that particular task uploading, it will be your energy consumption. You know, the impact of CO2 emission by cloud servers is always a vital issue. This already I discussed it. Fog computing is always viable solution towards the reduced power consumption, and this leads to the issue of the selection of the energy efficient application. This is very much important. However, there must be a trade-off between the power consumption and transmission delay. We are able to minimize it, both power consumption as well as the delay, but it's not like this. In order to reduce the delay, it's okay, our power consumption it will be increased. It's not like this. It's okay. So there has to be some trade-off between the power consumption and the transmission delay. Other resource management issues, it will be the resource sharing to provide services to the end users with benefits. All the resources need to be shared. And finally, it will be the proactive caching. The content of the upcoming tasks are predicted and prefaced during the current task. Actually, in this particular area, now many research work are being carried out, because there is a chance of application of the ML techniques, which particular upcoming tasks they actually require to like task uploading. So we are supposed to predict it. So the content of the upcoming tasks are predicted and the prefaced during the current task execution. It reduces the burden on access link by the computing results in advance without any prefaced content of the tasks. That's why already CDN, with the help of the CDM, I have already discussed it. Now, whenever you are trying to design any task uploading algorithm, you are supposed to go stage wise. First, it will be the model descriptions. You are supposed to design your model, and under that model, there will be fog model, there may be latency model, and there will be energy model. It's okay. So your fog model, energy model, and latency model, fog model fine, may not be limited mathematics, but when you are dealing with the energy model and latency model, you may have the tricky mathematics here. I'll try to illustrate by means of an example. Once the models are fixed, then based on the energy model or latency model or the fog model, you are supposed to formulate your task uploading problem in the form of a constant or non-constant, unconstrained optimization, right? And that particular optimization problem, that may be in the form of linear programming problem, maybe in the form of integer linear programming problem, maybe in the non-linear programming problem as well. Once the problem formulation is over, then you are supposed to solve it, and for that you are supposed to apply some kind of the optimization techniques. This may be the traditional, but the traditional optimization techniques may have some kind of the limitation in order to solve a complex task uploading problem, which is in the form of LPP or ILP or non-LP. That's why different kind of the advanced optimization technique are being applied. Say let it be your Karus container condition or Karus container method, or let it be Lioponev method, or let it be your game theory based method, or let it be any meta heuristic approaches, because like uh, number of meta heuristic approaches has also been proposed in order to solve the task completing problem, or it may be some kind of the heuristic, and again under the meta heuristic approaches, there are a lot of variations. It may be the nature inspired, it may be your evolutionary computing based, right? Or other kind of the approaches, let it be MADM or MCDM, which are being also used just to solve the task completing problem. So once you propose that particular method to solve your formulated task uploading problem, right, then you are supposed to judge its quality result or the performance measurement by simulation. It's okay. And this simulation results must also be compared with the state of algorithms, and in that case just comparison of the results with the help of the bar chart for some kind of the performance metrics, say let it be delay, energy consumption, etc., etc., it will not work. We require some kind of the statistical techniques, let it be ANOVA, chi-square test, or let it be post hoc analysis. We are supposed to uh, employ all these statistical method to for the fair comparison of the simulation results along with the state of arts algorithm. It's okay. So these are the three stages. First it will be your model description. Under model description, fog model, energy model, and latency model. It's okay. This model may be optional, because whenever fog model is mandate and latency model is mandate, because wherever there is a task uploading, we require a latency issue. Because of the latency issue, fog has been employed. So along with the fog model, latency model is very much important, whereas this model may be optional. You may not take care about the energy as a parameter. It's okay. Rather than energy model, you can have a cost model as well. So once the model is completed, then you are supposed to formulate the task uploading problem as an constant optimization or unconstant optimization problem. Once it is formulated, then you can apply some kind of the optimization technique, as I already said. Maybe the game theoretical based, maybe some kind of the meta heuristic approaches, or you can develop your own heuristic. And then once you apply it, you are able to simulate, you can test your proposed method with some kind of the data. You can have the simulation results, and then you compare the simulation result with the state of art algorithm, and fair comparison can be made with the help of the some kind of the statistical method, as I already told to you. It's okay. And number of task completing schemes have been proposed in the recent years, quite a few here. And I can have a look. For the case of the matrix, it will be energy and delay, and then here it is load balancing issue, then incentive computation, then here it is computation, incentive computation, like this. It's okay. Then here it is computation, energy consumption, like all this work. And these are the results. This is the strength and this is the weakness of all the proposed algorithm. All right. And then I'll try to illustrate the previous methods for a very popular task completing algorithm that is popularly known as FAMTO. So I'll go for the fog model, I'll go for the energy model, I'll go for the latency model. I'll show you how to formulate the constant optimization problem, the simulation result, and etc. Or I'll not discuss about the proposed method. Okay, so these two, how to formulate a constant optimization problem for a task uploading, that is my main target in the rest of the presentation. So this is basically known as a fair energy minimized task uploading FAMTO, and this is not very old because it has been published in 2018, right? FAMTO, this is the fair and energy minimized task uploading for fog enabled IoT networks, right? The basic objective of this paper is to minimize the overall energy consumption during task uploading services in a fog enabled IoT networks while taking care of the transmission delay, right? So transmission delay, that must be taken care, and above that we are trying to reduce the overall energy consumption. So we require energy model and fog model both, delay model both, latency model and energy model. Along with that, there is a fog model as well. Fog model means what would be the fog nodes, how the task it will be taken care by means of the fog node. Is it okay? How much part it will be taken care by means of the end devices, how much part it will be taken care by means of the fog devices, that we are supposed to do it. And under the fog model, we have a collection of the fog nodes, and there is a virtual controller, and this is a collection of the terminal nodes, and we are able to divide the whole area into two planes. One, it will be the virtual controller plane, and another it will be the service plane, right? And in the virtual controller plane, note that virtual controller, it will be really independent of the terminal devices. Is it okay? Terminal devices. And then service plane and then virtual controller has a common area, that is the fog node, right? Suppose a task is to be uploaded from the TN to the fog node, am I right? So the virtual controller will decide out of the 4 fog nodes which one will be selected for the task uploading from the TN to that particular fog node. It's okay. This is the service plane, right? This is the whole service plane. So the virtual controller also decide how much part of the task to be executed by means of the TN and how much part, rest of the part, it will be taken care by means of the fog node. It's okay, depending on latency, minimum latency and minimum energy consumption. So we have actually decided the problem given a set of the terminal nodes and set of fog nodes. This is our fog model. Whenever a task, particular terminal nodes wants to upload the task, then the virtual controller will select out of number of fog nodes a specific fog node which can upload the particular task in a minimum delay, with minimum delay and minimum energy consumption. And not only that, how much part it will be taken care by means of the terminal node and how much part it will be taken care by means of the fog node. Is okay. And again, in our fog mode, we can use the heterogeneous fog nodes. Some of the fog nodes may be the passive and some it will be the active. Is it okay? Some it will be the active. So for the case of the passive fog node, they are actually battery operated, but active nodes, they are powered cable. Am I right? Yeah, look, this fog node I and this fog node, that is the battery operated. So they have the limitation. It's okay, but they, so energy consumption for the case of the battery operated fog node is really severe than that of the cabled power active nodes. Is it okay? And again, it indicates FN idle. They're all the idle, all four fog nodes are idle, and cross, oh, this is active, this is busy. So you cannot allocate this particular for the task operating. Out of 4, only 3 it will be there. So this is our fog model, right? So a fog cluster consisting of the n heterogeneous FNs, a virtual controller providing task operating service to the TNs. The active FNs are cable powered, the passive FNs are battery powered and so sensitive to energy consumption. So this is our fog model. Now let us look for the task operating problem, where actually this is, so rather than describing here, you come to that particular point. That the TN has L bits task, right? All total L bits task is there, and this L bit task has been divided into 2 parts. One, it will be LT bits, which will be taken care by means of the TN itself. So LT part, it will be taken care, it will be executed by the terminal node itself, and then LI part, it will be taken care by means of your what should we call it, by means of the fog node 2. Is okay. So this LI part, that is the L2 part, it will be taken care by means of fog node 2. I have shown you the example. It may be the fog node 3, maybe the fog node 1. So we are supposed to decide it, right? Which is most important, LT does not vary, but LI really varies because number of FNs are there. Is it okay? Number of FNs are there. So they are the some kind of the terminologies. Say for example, L, that is the total bit, overall task size of the TN. Then Dmax, it will be the upper bound of the task delay, and Pmax, it will be the upper bound of the transmission power of the TN. LI bit, it will be subtask size downloaded to uploaded to FNI, and LT bit, it will be subtask size processed locally at the TN, and eta tau, it will be your CPU cycle, but it will be processing 1 bit data at the terminal node. And eta I, again, this is the 1 bit data. This is the CPU cycle for processing 1 bit data at FNI. It's okay. And the FT, it will be your CPU frequency. FI, it will be the frequency of the fog node. All these are the, it's okay. All these are the things it will be taken care. Now let us try to use all these terminologies in order to formulate our energy and as well as the delay. Your task delay includes 2 parts. First, it will be delay for processing local processing. Local processing delay of the task with LT bits. As I already told, LT bits, it will be taken care by means of the end devices itself. And then it's also uploading delay. Uploading, what I told, transmission of LI bits and LI bits to be executed by means of the fog node and sending the result. But sending the result, since it will be 1 unit, so that particular delay, that we are able to avoid it. So basically the uploading delay, I want to mean transmitting the LI bits from the TN to the fog node and execution of its LI bit, because sending the result, which will be 1 unit, that we are able to avoid it. So the uploading delay, basically it will be the time for transmitting LI bits to the fog node FNI, and the time the FNI will take to process it. That's all. right? So overall task delay, it will be the max of dt and then di is okay. So what is this dt? This is for the local processing. This is the local processing by the terminal node itself. As I already told that eta t, it was the CPU cycle for 1 bit. So for the LT, it will be multiplied. And since the frequency is ft, so it will be divided by, that way we are able to calculate the delay. It's okay. So this is the total number of processing time, right, to process LT bit with the CPU cycle time, CPU cycles eta t per 1 bit, and it is divided by the frequency. So we'll get that particular delay, right? Similarly, for the case of the task uploading delay, di by means of the fni, that can be expressed here. Di is equal to li by w by bi plus, this is the delay, and then this is the processing time. Sorry, this is the processing time, and this is the transmission. It's okay. This is the transmission of the li bit. Okay. So this is the transmission and this is the processing by means of the fni. Okay. So energy consumption, next you come. Energy consumption, it will be energy consumed by the terminal node in processing LT bits, and again energy required to transmit LI bits to the FNI, and again energy consumed by FNI in order to process the LI bits. So these three things it will be added. But the first of all, transmission energy consumed by TN in processing LT bits and transmission of LI bits, which is actually indicated by means of ET. It's okay, ET. And then this particular thing, energy consumption by FNI, that is indicated by means of PI. And this is the total expression. And again, BI, it will be your log normal form. We are able to take care about it. For the rigorous mathematics, you can follow that particular paper, femto, right? Now let us have a look. So what will be the overall task delay? L, it was LT plus LI. So if we substitute the values of LT and then LI from these two things, then we are able to get D is equal to max of this much. Is it okay? And similarly, energy consumption, if we sum of them, then we can have E is equal to this expression. So we have actually expressed the delay and energy in terms of LI and PI, which is really variable, very important, right? And LI depends on the FNI, PI depends on FNI. So LI and PI. So what is that particular problem now? We are supposed to upload the subtask LT to a single FN whenever multiple FNs are there, multiple idle FNs are there. So which particular FN will be selected for the task uploading? It actually depends on the values of LI and PI. As I already said, LI and PI. However, LI and PI vary from FN to FN. So we require the minimum delay and we require the minimum energy consumption. Based on that, FNI to be selected, and in that energy consumption and delay, it will be really varied. So here we are able to do like this problem formulation. We are supposed to select that particular FNI which minimizes the local energy consumption, and in the constant we are supposed to take care about the delay as well. So minimum of LI and over PI, this is what? This is the delay. Sorry, energy consumption. So this is the expression for the energy consumption. Clear? This is the energy consumption. So we are supposed to minimize it, right? Keeping in the mind our delay should be less or equal to Dmax, right? So we are supposed to select that FNI which minimizes the total energy consumption, that is minimum over Li and Pi, this expression for the energy, such that your delay should not exceed the maximum delay, and your Pi, that is the power consumption, should not exceed the maximum power. And of course, this Li, which is a part of the original task consisting of L number of bits, must also not exceed the value of L. So Li should be fraction. Li is lesser equal to L, right? So this way just we are able to formulate it. Now once this is formulated, we are supposed to apply some kind of optimization techniques or meta heuristic approach, or we are able to apply your what should you call it, uh, any heuristic technique, or let it be your game theoretical approach, or let it be MCDM, or let it be MADM, etc. That we are able to do it. Okay. So so the previous one I discussed that how to formulate it. We have first discussed about the Fock model. Then I showed you how to formulate the expression for the energy and as well as the delay. And finally, we have formulated the problem in the form of a, this is basically a nonlinear optimization, constant optimization problem. Nonlinear, why it is so? Because the expression to be minimized, that is non-linear. This is non-linear. Is it okay? So this is the non-linear programming formulation. We have showed it, and I discussed that once this is actually formulated, then you are supposed to apply some kind of the optimization technique. Okay. Now let us consider the other kind of the method. You know, the main task uploading, we are able to think like this. You have been given a number of terminal nodes and quite a few fog nodes are there. Number of terminal nodes, it will be much higher than that of the fog nodes, right? And the terminal nodes, they are supposed to upload their task to a specific fog node. It's okay. So why shouldn't it apply some kind of the clustering of the terminal nodes surrounding the fog nodes? That way we are able to develop the task uploading algorithm as well. So here is a scenario. Say let it be phi 10, that is a fog node, 10th fog node. And then then the terminal nodes, let it be E22, E23 and E24, they are all connected to the fog node phi 10 through wireless link. Is it okay? Whenever E23 is only connected to the fog node phi 10, E24 has the connectivity with the two fog nodes phi 10 as well as the phi 9. So whenever E24 will upload the task, whether it will decide to join to the phi 10 or it will join to the phi 9. It's okay. Our task uploading technique must take care whether E24 will upload the task to the phi 10 or it will be depending on the QS parameter. The QS parameter first, it will be definitely the delay, and apart from the delay, it may be the energy, maybe the cost, maybe anything else, right? So based on the particular factors, we are able to cluster all the, you know, the fog, terminal nodes surrounding the fog nodes. So if we cluster, the result may be like this. Look here, all these three guys have actually joined to the fog node F10, phi 10. Yeah. Similarly, for phi 9, there are four. Phi 9, these four guys will be there. Is it okay? Now, while you are actually performing the clustering, you are supposed to take care of the other as well. You know, if we consider all the fog nodes are homogeneous in nature, Sanjay, how much time more I should actually consider it?
Sir, 15-20 minutes more, sir.
Okay, then. So while actually considering the clustering, quite a few things we are supposed to take care. First of all, if we consider the fog nodes, it will be the homogeneous. Then we are supposed to take care about the load balancing of there. You see, for example, your phi 10, the fog node has got the task uploading to be taken care from the four end devices, whereas the phi 13 is really relaxed. Phi 13 has only got it one. So we require the load balancing of it. This is the first thing. Rather, if it is heterogeneous, so the capacity of the phi 10, it is lesser than that of the phi 9, then let the phi 9 to be overloaded than the phi 10. So if we consider, so whenever it will be heterogeneity, rather than load balancing, this may be the unequal clustering. But we must take care the capability of that particular specific fog node. It may happen that phi 13 is much higher than that of the phi 12, but unfortunately phi 13 has got only one fog terminal node. This should not actually happen. So whenever the heterogeneity comes into picture, it actually increases the complexity. Now, once it is clustered, so task uploading it will start taking. So what will happen whenever all three they will try to upload the task to the phi 10? Am I right? Or let it be here for phi 14, whenever all the four task node terminal nodes they start uploading here, what will happen? Here is we are able to apply some kind of the queuing theory or the queuing model. We are able to form a queue between the request, and depending on the priority of the task node, we are able to serve that. So this queuing theory, queuing model, that may be multi-channel, maybe the single channel, etc., etc. So there is a question. So the people have started applying the queuing theory here also. Is it okay? That we are able to take care about the task uploading, right? So this is what about the clustering technique. Some the people are also applying number of evolutionary techniques, especially the nature-inspired algorithm, etc., etc. It's okay. Now I'll enter into the applications of the fog computing. You know, today's smart cities have number of services. So there may be smart transportation. It's okay. Then waste management, then water management and greenhouse control, and there is a tremendous role of number of IoT devices. So for smart cities, we are able to employ the, so here is a scenario for it. This is the fog computing are heavily being used just to solve the smart cities problem. This is the scenario. It's okay. Number of things it will be taken care of. Say here it is smart house, then biomass fuels, EV car gearing, the smart house, then electric bus. Is okay. So quite a few fields I have already: smart transportation, waste management, then water management, greenhouse gas control, etc., etc. So this is one of the great applications of the fog computing. Then smart transportation. Smart transportation. Intelligent smart transportation. What will happen? Urban environments are now overcrowded with vehicles, traffic, congestions, accidents, and pollution. These need to control, which depend on real-time feedback from roadside infrastructure, traffic flow, and passengers' activities. So fog computing is well suited for vehicular ad hoc network, for local decision-making mechanism. It's okay. Apart from the transportation system and smart city, we have our industry 4.0. You know that it has been launched in 18th century. This is the fourth industrial revolution, you can say, employs IoT. And this nebula technology has actually launched as a for computing platform for just to support the industry 4.0. Okay. So smart transportation already told, and this is the scenario I told you. Look here, your fog server that is in the form of the access points are there. So your car has sensors. It actually continuously sends the data in the fog server. It analyzes and can give some kind of the signal to here. So whenever your car is in jam, but you make your car on, then it can send the signal, please off your car, just putting some kind of sound or something like this. But the sensor nodes must be deployed inside your car. The sensor nodes, they can actually, and your sensor node can also send some kind of the data, right, which may not, so say for example, it can take the continuous video of your eye condition. If you feel that you are drowsing, it's okay, it can send that particular data. So you are feeling sleepy, right, you are feeling asleep, so it can analyze the data and can send kind of the signal to you, right. So these are all the parts of the intelligent transportation system, as I already told. And then making the different route, like just to avoid the traffic congestion, etc. All these are the taken care, right. Now healthcare is a huge applications, and no smart based service called emergency help alert mobile has been introduced. This is a fog computing platform, especially for the old care, the healthcare of the old people. Each data is pre-processed in the smartphones, monitoring of the patients and activities of nurses in a hospital. So these healthcare facilities, this is EHAMC as a fog computing platform has been launched, and they are actually working, right. So this is basically a body wireless sensor network. There may be some number of wearable devices, so or sensor nodes. Your sensor nodes may sense your pulse rate or let it be blood pressure, and can send the data continuously to the local server. Local server means that is the fog node, and that particular server can analyze the data and can send some kind of the warning message to your smartwatch that okay, now you should take rest, you should not put much effort in the gym, right. Here it is in the gym, is it okay, like this, because number of accidents has also happened in the gym itself, especially heart collapse, etc, etc, even the young people. Now finally I'll come to the open research for the issues. First of all, I told you application uploading. So application uploading is not always efficient. What is the reason behind it? This is due to the lack of available resources in fog layer. Then it comes into the resource management. More efficient resource management, as the fog computing does not enough computing and storage resources. And heterogeneity, that is one of the hindrance for the development of the task uploading algorithm. Your bottommost layer of the fog consists of various and devices that I already spoke to you. Devices with heterogeneity of data collection, data format, and data processing capability. Their configuration may be very different. You may have the different configured smartphones, smartwatch, etc. Then, of course, among all, security is very much important. So we require to standardize. It's okay. Standardization is required so that various IoT systems can securely interact each other and cloud server. Okay. Now the people are also performing the research on the software-defined network based for computing.
Excuse me, sir.
Please.
Sir, good evening, sir. This is
Good
Sadhu Mishra from ITM University, sir. Sir, I have one question regarding
evening.
this, that there's a cloud computing and fog computing. So as when we talk about the cloud computing, so there is the cloud service provider. So similarly, in case of fog computing also, there is a fog computing platforms also, sir.
Yeah. Now, for the cloud service, there is a CSP, definitely, cloud service provider, which will
Okay.
be owned by means of the large companies. But
Yes,
you
sir.
know that whenever a task is actually requested by means of the terminal nodes, rather than sending the request directly to the cloud server, it goes to the fog node, local fog node, right? And these fog nodes that can be owned by any private company. So they may not be like the CSPs. The CSP has no role. This can be
So
maintained by means of the private companies.
it's a part of cloud computing, sir. Can we say it like this or not?
I told you the fog layer, it actually creates a mini cloud. It provides similar kind of the services to the end device users, but with the close proximity to that, means that is at the edge, at the very close to the bottom layer.
So different servers would be, that means independent servers would be on that particular
There may be a
computing.
server, but
Yes.
these servers in the fog layer that may not be as much strong or powerful like the cloud server.
Okay, sir.
Is it
So
okay?
it's yes, sir. Sir, its cost would be very high as
Which,
compared to cloud computing, sir. As what it would be, sir.
whenever
I'm
you are
very new
using,
in this field and I don't have much more knowledge. So that's why I want to clear these things from you, sir.
yeah, no issue. So let me complete, and then you can put again your question. Is
Okay,
it
sir.
okay?
Okay, sir. Thank you
Ah,
very much, sir.
okay. So the people are actually working with the software defined network. Actually, the example for the case of the femto, which I actually discussed with you, that is based on the SDN platform. In the SDN platform, you have a virtual controller, there is a service plane, there is a fog plane. It's okay. And then service plane, it will be like that service plane contains the fog nodes and as well as your terminal nodes, and virtual plane that controls your virtual controller and also part of the fog nodes, as I already told. So this is the part of the SDN, software defined network. But which is very much important, it can have the local coordinator, a local coordinator required to handle the dynamic service requirement, that is your virtual controller. And then controller design, this is very important. The fog SDN controllers need to cooperate among themselves to efficiently handle the limited fog resources and implementation of the test bed due to the sense. So there are all the three things to be taken care for the case of the research in the SDN based fog computing. Other issues may be reliability, that is the fault tolerance. Fault tolerance, I told any uh, fault should not be catastrophic. Understand? Then we can have some real-time analysis. Here is a tremendous role of the ML, machine learning algorithms. Then I told you, like fog nodes, usually they are fixed because you are using the server, you are using the fog node access points, you are using the gateways, they are basically fixed. But unless we move, allow them to move from one location to other, so we may not obtain the flexible services from the fog node. So this is another challenging issue, mobility of the fog nodes. Mobility of the IoT devices, no problem. Your camera, you can take from one place to another. Still, you are connected with the access points, right? Your mobile phone may be connected from one tower to another tower. So, mobility of the IoT devices will be there, but mobility of the fog nodes, that is really challenging. Whenever the fog computing allows the mobility of the fog nodes, then we'll get huge, means flexible services from the fog computer. It's okay. So they're all the open research challenges. This is some references are there, right? My presentation is mainly based on the paper Mithun Mukherjee, Survey of Fog Computing, and this is IEEE Communication Service and Tutorials. A very good paper. Anybody can treat this is the key paper to learn the fog computing research. And apart from this, there is a another. It will be a comprehensive survey of the fog computing. This is another. You will get a very good architecture site here, right? Very good architecture site. And then for the task uploading, there is a paper in the future generation. I can't see here because of the I wanted to make it limited number of slides, right? If you just type it, the survey on task computing in fog computing in the Science Direct, you will get that particular paper in the future generation. It's okay. That's not bad. Good. But the best paper, I feel that this is from the Mithun Mukherjee. It's okay. So this is 2018, and FAMTO is also there in the 2018. So from there also I have borrowed to prepare my presentation. It's okay. Now